Yes.
Go for question 2 and homework 4, please.
Which homework for? This homework, I like our homework for,
Oh,
as opposed to like a past homework for.
yes.
Okay. Question 2 homework. This is the one where if G is a group and H is a subgroup, such the index is 2, then it's normal. Is that the?
Yeah, and then it's the same pure being necessary.
Okay, so. Suppose we have a subgroup, H and G, and so our first task is show that H is normal. What does it mean to be for a subgroup to be normal?
G, conjugate, and so on.
Right. So I gave you a bunch of things. I never really showed you that they were equivalent. Well, maybe I did on one of them. But anyway, so there's several ways we can pick normality. Now the real definition is this. One, for all G and G, the inverse in G equals N. Right? That was the definition that I first gave you on this compromise. And then I also said in that definition that this is equivalent to all G and G, N and N, that and this one's kind of a workaday thing, right? But there's actually another condition. Does anybody? There's another thing that we talked about. There's a third. Well, actually, probably one of this. And this one actually is going to help us when it comes to trying to tackle this problem right here.
Is it that the left sub or the left coset equals right coset?
That's right. Every left coset is also a right coset. That's another one of these things, right? For all G and G, so GN is the same thing as G, right? This is the easiest one. Number 3 is the easiest one to implement this particular problem. Right? What does it mean for the index of H and G to be 2? It means there's 2 cosets, that's it. And I know what one of the cosets is, right? It's H, right? Exactly. 2 left cosets. So basically what that says is the subgroup H occupies half of G. Half of G is in H and the other half ain't, right? So here's what the cosets are. One coset is H itself. And the other coset is XH. And what is X? X is anything that is in G, but not in H. So X is just something that comes out of the other half, right? See what H gets. It's like half of it. Just pick anything that's not in H, and that is, there's my disobedience. Pick any element of G that's not in H, and this will be the coset. Okay, because remember, everything in G is in one of these 2 things. So if it ain't in here, it's in here, right? So anything that's not in H will do. There's nothing special about left. Agreed? I could have done this if this way. Now remember, since X is not an H, it's still not an H here. Now notice that G and this is a disjoint union in the sense that H and XH have nothing in common. Agreed? So what can we conclude from this? That's right. It must be the case. This is H and this is the other half. This is H, this is also the other half. So the other halves have to be equal. Everybody agree with that? And there you go. So H is normal to G. But that's right. That's yes.
You have to take that last step from you defining those two sets of cosets as unique. Could you say H must be equal to H, therefore XH must be equal to
Yeah, sure. I took this approach because I thought it might be more eliminating, but yeah, sure. There's a lot of ways to skip this gap. This seems like kind of easy once you see how to do it, right? Half of it is the other cosets, the other coset must equal left and right. This does not work for any fraction that's smaller than a half, right? So I think the other part of the question was, is this true? Did I ask specifically, is this true for three, right? It's not. It is possible for the index to be three, but H is not one. That is certainly a possibility. Can anybody give me an example? Okay, first thing, if you're thinking about algebra, you're looking for an example of a subgroup that's not normal. That's first and foremost, right? What you're looking for, right? Better not be an abelian group, right? Because any subgroup of an abelian group is always normal. So looking at abelian groups, that's guaranteed to be fruitless. What's the smallest group that's not abelian that you can think of? Oh, yeah. Absolutely. Dihedral on the triangle. I've got another name for that. The dihedral on the triangle is actually S3. They actually turn out to be the same. That's an interesting thing for you. The dihedral group on the triangle and S3 are the same group. They're both groups 4-6. You can see they behave the same way. The triangle is the biggest object in which those two are the same, right? By the time you get to a square, there's only 8 elements in S4. I'm sorry. There's only 8 elements in D4, right? But in S4, there's 24. Sorry. So let's look at S3. So I'll write down elements. These. If this thing has a subgroup of index 3, what would the order of the subgroup have to be? If its index is 3, its order would have to be what?
Also pretty effective.
Well, so think of it this way. This is essentially Lagrange's theorem. Remember, the index of a subgroup in the group G is the order of G divided by the order of H, right? So if I want that to be 3, and this is 6, the subgroup would have to have order 2, right? Everybody agree with that? Can anybody find a subgroup in S3 of order 2? It's got exactly 2 elements in it. Ooh. I'll take the easy one. If it's a subgroup, it better have that in it. You know, is there a subgroup order 2? That'll work. It's pretty easy to see this is a subgroup, right? Because when you multiply that by itself, you get the identity. This times this is 1, 2, and so on. And in fact, there's nothing special about 1, 2. E in 1, 3 is a subgroup. E in 2, 3. So they're all subgroups too. Is it normal? Well, no. So, no. 1, 2 is in H. And almost anything that I think of as 3 will work. Well, let's do this. 1 goes to 3, back to 1, so 1's left alone. So I'll start with 2. No 2. 2 goes to 1 to 3. 3 better go to 2. It goes to 1 to 2, and it's done. There you go. And this is not an H. So H is not one. So there's an example of subgroup index 3 that's not one. Yes,
Why did 1, 3 inverse just become 1, 3?
because what's 1, 3 times 1, 3? Well, let's do it. Where does 1 go?
3.
But then,
3 goes back to 1.
there you go. So 1 goes to itself. There's no 2, there's no other number except 3. Where does 3 go? It goes to 1.
Why does that show that the inverse is just?
Because what this does is the identity. Right? At the end of the day, 1 goes to 1, 3 goes to 3, everything else goes to itself. That means 1, 3 is its own inverse.
Okay.
Right? And think about what 1, 3 is. That's actually a transposition in the language that we talked about today. What you're doing is you're taking 2 objects and swapping. If you do that, if you swap 2 things and then you swap the same 2 things back, you're back to where you started. Right? Does that make sense?
Yeah.
How many of y'all feel comfortable doing these calculations with the cycles? Should we give one of those a whirl, maybe? All right, so let's see. Let's have a. I don't know. All right, yes. Let's see if we can figure this out. Let's figure out what happens this time. Y'all put your eyeballs on this and tell me where does well, I'll start with 1. Where does 1?
5. Okay, 1.
I think you're
5
right.
goes to 7. 7.
Really? I believe your first answer. I better check. I better
1
check
goes to
myself.
5. 5 goes to 3. 3 goes to 2. 2 goes to 4. Skips that one. 4 goes to 5. That was great. Right?
How many of you see that? Well, 1 goes to 5. So it's a mystery for you, or is it okay? Right. It does its dance. 1 goes to 5, then to 3, then to 3, then to 2, It's 4, no 4, then to 5, and the end of its journey is 5. Now, pick this up where you left off. Where does 5 go? Where's it go? Yeah, it goes back to 1. So 5 goes to 6, goes to 3, to 1. Okay, now I'm not done. That's why I start at 1. You can actually do this in any random kabuki order that you want. I just like to be an accountant. So I finish the cycle, I've come back to where I've done, close up parentheses off, new chapter. What's the smallest number that appears in one of those cycles that I haven't seen yet? 2, right? Everybody agree with that? Okay, where does 2 go?
7.
Everybody see? By the way, what would happen if I got 2 went to 5? I did it as what would happen if I did this mess and I said, oh, 2 goes to 5? Well, that means I did something wrong. I better check it over, right? I either did something wrong back here or here. Because when you do this algorithm, you should never see a repeated number. Right? So that's a big kind of warning sign. If you get a number you've seen before, if I had started 2 and ended up with either 1 or 5, that means I messed up. How about 7? Where does that go? Yeah, 7 was easy because it only appears in this first one, so it just goes to 3. How about 3?
4.
3 goes. I agree. How about 4?
No. 8.
8. How about 8?
30.
Right. There's no 8s until I get here. It goes to 1, then to 2. That closes off that cycle. Am I done? Okay, what's the smallest number that appears that I haven't seen yet? Looks like 6. And it looks like I'm out of numbers, so where does 6 have to go?
So
It better go to itself. Well, let's check it just to make sure. 6 goes to 2, 1, 2, 6, and it's done. Okay. Everybody agree with that? So that big mess of jumbly stuff can actually be written in small form. Let me ask you this. That is an element. That element I gave you is in S8. Everybody agree with that? Because all the numbers between one, it's in S, actually it's in S9, it's in S10, it's in S11 as well. But anything that's 8 or bigger, right? Everybody agree with it? But we'll just pretend this is in S8. What is the order of this element?
Okay.
That is correct. How do you get that?
Here's one like sub function of order 5 and another order 2. So to bring both of those back to what they start with, you have to have a multiple of both 2 and 5.
That's right. Y'all remember that homework where we talked about elements of a group, and if x times y equals y times x, then the order of x, y is the least common multiple, or it divides the least common multiple of the order of x, the order of y, right? And actually, for this one, it's stronger than that. Whenever you decompose something, when you get it in terms of disjoint cycles like this, it's the least common multiple of cycles. That's order 2, order 5, order 1, and the least common multiple of those. So the order of that element, that's a little element of order 10. Any questions? Y'all feel pretty comfortable with that? Yes.
Can you talk more about like the intuition behind group actions rather than just like the definition? Does that make sense?
Well, the idea behind group actions is And we're gonna be studying this. In fact, there's a whole section called group actions that we haven't got to yet. I mean, I've introduced you to what the concept is, and the one real application that I gave you some examples. Oh, here's some cool stuff. The one real application we had was Cauchy's theorem. Anybody want to remind me what Cauchy's theorem says?
There's a positive prime that divides n, which is the order of a finite group. And there's the cardinality of x equals the positive prime.
There's an element of order.
Yeah.
Right. So if you have a finite group with of order n, and if there's a prime that divides n, then there has to be an element in that group of that prime order, right? That's Cauchy's theorem. That's the only place that we've really applied group actions really stringently there. And when we did it in the proof of that. But one of the group actions that you can have is, and you're going to see the applications of this because we're going to use it to basically take apart groups and look at how their structure works using group action. But here's kind of a concrete example. Actually, you know what? I'm going to do the hexagon just like I did today in class, but I'm going to do it differently. This is again going to be a if you remember today from the, so this is my group actions example. I'm going to do this differently just to kind of give you a different perspective. If you remember today, do you all remember that I did this hexagon thing in class? I talked about that. If you remember, I put vertices on the y-axis, right? And now instead of putting vertices here, I spread them out like this. So here, the rotation, if you rotate 60 degrees clockwise, that's still 1, 2, 3, 4, 5, 6. But the S now actually looks different than what we got for us today. What happens when I flip this around the y-axis? 1 and 6 swap, 2 and 5 swap, 3 and 4 swap. Do I agree with that? So this group, the group generated by this, acts on this hexagon just by doing what these functions tell us to do. So the element R in this group, how does it act on this figure? By turning it clockwise 60 degrees, right? How does R squared act on this? By turning it clockwise 60 degrees twice, right? So this group basically so this group action, you can think of this geometrically. This is let me make something up here. If I had R S squared S R, right? Actually, this will help us practice do this. Let me do this computation. S is 1,625,4. Here's S 1,625,34, and then the market. I'm a lazy man, and I would rather not write 2 6 cycles and then do 3 cycles. So can somebody tell me what is R squared? Can you look at this and tell me this is what R is? It takes 1 to 2, it takes 2 to 3, 3 to 4, 4 to 5, 5 to 6. What does R squared do?
5.
R squared, that's right. R just jumps 1. R squared jumps 2. Jump 2. I mean, jump 2. 2. So it actually should look like this. I agree. That's what R squared should be, right? I agree with it. Okay, let's do a gut check on this. Just look at this element right here. What's the order of this element? It's 3, the least common multiple of its disjoint cycles, right? What's the order of the original R? It was 6. Now we did R squared and it's now got order 3. That kind of makes sense, doesn't it? Right? Your original one had order 6, we squared, it's now got order 3. So I'm feeling, pretty proud of myself. So how about R cubed? I would guess what R cubed does is that's R squared, R cubed. So let's jump 3 and then 1, 2, 3. Oh, wow. So it swaps 1 and 4, 2 and 5, and 3 and 6. So 1 and 4, 2 and 5, and 3, 6. And this bit is R cubed. Everybody agree with that? What's the order of R cubed? It's 2. Please come up with it. So this is making good, wholesome, clean American sense. So what does this do? What is this at the end of the day? Well, this is more practice. Where does 1 go when it does some things here? Let's do. Okay, maybe let's see. 1 goes to 4, then to 3, then to 5, and then to 2. I agree. Can you already tell what it is? You don't. In fact, it's got to be one of a couple things, right? 1's already gone to 2. So if this is an action, if this rotates this, it's either this rotation. What else could it be? Does it have to be this rotation or 1 goes to 2?
Back to it swallows.
You could actually flip it this way. That's a possibility. Let's see what happens. Where does 2 go? It looks like it goes to 3, so it looks like it is the rotation. So it looks like where does 2? 2 goes to 5, to 2, to 4, to 3. Now this is really so it looks like 1 goes to 2, 2 goes to 3. So I think that's kind of it. Better go after this 4, 5, 6. So it looks like I accidentally sort of got just the single rotation, right? Let's see what happens. 3 goes to 6, 1 to 3 to 4. 4 goes to 1, 6 to 2 to 5. 5 goes to 2, back to 5, to 1, 6. And 6 goes to 3, 4, 6, to 1. So if I do these things, what it does is it'll do all these actions. But at the end of the day, what happens is I get this. So I've just done a spin of, I've just done a 60-degree clockwise spin of that. Here's another really good example of group actions that you see. It's all of 3110, right? What did you do? Well, we want our matrices to be invertible. I mean, you did linear transformations, but assuming that you have linear transformations, Let's just say on R2, right? So you've got 2 by 2 matrices and the determinant is not zero. So they're all invertible. That gives you an action of that group there, the 2 by 2 invertible matrices acts on R2. And how does it act? By multiplying the vector.
Question?
Yes.
If we were given a question that was like, there's some word made of S's and R's, what is its final product? Could we justify an answer by using
The dihedral relations.
the order of individual components and say it must be formed from elements of length 2 and 3, therefore it has that order 6?
Not unless you know that those elements order 2 and 3 actually commute with each other. That's really the problem. So this is an n cycle, right? So the order of this would be n. N could be anything, 27, 5, 8, 6, 7, 5, 3, 0, 9, whatever I want. This can be anything, right? You can actually write this, and let me show you why this is true. Where does 1 go? It goes to 2, and then nothing, there's no 2's up here because it's all 1's and things bigger than 2. So 1 goes to 2. Where does 2 go? It goes to 1, is immediately kicked back to 3, and there's nothing higher than 3 here. So it goes to 3. Where does 3 go? 3 goes to 1, immediately kicked back to 4, nothing higher than 4, like this. And in fact, in the end game, where does n minus 1 go? Well, there was no n minus 1's up until here. N minus 1 goes to 1 and is kicked back to n, and then n goes to 1. Here's the problem. This could be like some huge not odd number, like 137 could be n, and these are all elements order 2, right? And so this least common multiple stuff doesn't work unless you know that the elements commute. And that's the problem, because those elements in there, those aren't disjoint cycles, and so they don't commute, and so you can build just any wicked thing you want out of it. Okay. So for example, consider this is a group that I'm quite sure in linear algebra they didn't talk about group actions, but that's actually something that you were doing there when you were in 3110. If you look, so that fancy notation of GL2R, I just mean 2 by 2 matrices where the determinant is not 0. So these are all invertible, right? And it's very valuable to know how these linear transformations work. I mean, you use this in like, resolution on your computer screen. I mean, the linear transformations used all over the place. And the action is, so this is a vector in V2, or I'm sorry, in R2, right? So it's just, 2 coordinates, X and Y. And this is just, the action just means multiply that vector. That linear transformation will do something to that vector, right? It might stretch it, so it might rotate it, it might do a little of both. It might stretch it and turn it an angle, right? And this is an action because This is the way that matrix multiplication works with vectors. This is M1, M2 times B, which you probably learned at least implicitly in 3110 is this. That's one of the things, which is that's one of the things that you do for this. And also the identity. This is the identity matrix, right? The one that you multiply and it doesn't change anything. Notice that I acting on B is IB, which is B. That's all you need for group action. It's these two things right here.
So is an action always multiplication, like when you simplify it like that?
It can be translation. It can be lots of things. It just depends. I use my hands to have a group action on the Rubik's Cube when I solve it, because what I'm doing is I'm basically using my hands to perform functions on it that basically moves the rearrangements around, right? So a group action can be lots and lots of things. It's just anything that satisfies those two. Now, the examples I gave you are kind of some of the popular ones, right? Like rotating vectors or solving a Rubik's Cube or things of this nature.
Okay, so you define it that way, and then when whatever you define meets those conditions, it's a.
That's right. That's right. Right. The easiest group action that you might think of is like, in fact, I'll give you two examples. Let G be a group. G acts on itself. So here are two popular ways that a group acts on itself. Number one, G acts on itself, which is sometimes important because this group is important to understand the matrices themselves. One, by left multiplication, or sometimes it's called translation if the group is abelian. So that is, if G is in G and X is in G. So I think of this as the group and what's being acted on. Just do G acts on X is GX, right? I almost feel like I'm gonna take a shower. I feel dirty, like I'm getting away with something here, right? But I mean, that's all there is to it, right? And because of the fact that you have associativity of multiplication group, this is a group action, because if you look at G1 acting on, right, G1, G2, so acting on X, this is by definition G1, G2, X, because that's what we said it is. And because of the associative property, you get that, which is G1 acting on G2 acting on X. And two, the identity acting on X is EX, which is X. So there you go. Another important way that a group can act on itself is by conjugation. So again, I want to kind of steal my own notation here. So again, if G is in G and X is in G, then I'm going to find G acts on X by GX, G inverse. By the way, let me point out, if the group G is abelian, this action is trivial, right? Because if the group's abelian, then I can swap X and G, the G's cancel out, and I get G acting on X is just X, right? So this is only really interesting if groups not abelian. Well, let me verify that this works. If you have G1, G2 acting on X, this is G1, G2,
Right.
display X, G1, G2 inverse, right? That's what the rule says. Right, now I can massage this a little bit, right, because I can use the inverse to kind of turn that around a little bit. So this is G1, G2 X, G2 inverse, G1 inverse. Right, agree with that? Now let's kind of isolate this bit here. This is actually, isn't it? This is of course an element of G, so this is actually G1 acting on G2X, G2 inverse. Everybody agree with that? Because the definition says to do this circle thing, I put the G1 here and the G1 inverse there, right? And this thing in parentheses is also a bit of the action. Okay, so that works. And finally, if I have the identity acting on X, this is identity X, identity inverse, which is X. So again, that works. So that's a good example of an action. Okay, any questions on that? Did that get what you needed to get?
Yes, thank you.
Okay, other questions? It's
I can walk through homework 3, question 4, it goes through automorphisms. Almost 3 pages. It's 3 points.
okay, yes. Okay, so we define the automorphism group G. B. Well, we define all. I guess I can show it's pretty good before I start running my mouth. G group. G is a set of phi and G such a phi is an automorphism. Everybody okay? And somebody remind me what an automorphism is.
It maps to itself.
Okay, it maps to itself. G goes to G, right? So the domain and the target, or the codomain are the same thing. What else is it?
Nice.
I'm sorry, what?
Isomorphism.
It's an isomorphism. If you use it's an isomorphism. And what does isomorphism mean?
Adjective. Adjective.
It's bijective and it's a homomorphism. Everybody cool with that? Now, the first thing we need to do is show that all G is a group. Well, notice that P and Pitchfork, the and off G. Now I'm gonna get through a lot of this stuff pretty quickly. There's really, as far as showing there's a group, most of it's easy, but one thing is kind of subtle. Okay. This is a non-empty set. But I mean, that's the first thing that I might worry about is what if my set ought Z? What if there are no automorphisms? But there are. There's always one automorphism, please. Can you tell me what it is? The identity function, right? So if you have IG and GG, I capital G X equal X. This is the identity function. right? And notice that if you compose this with any other automorphism, you get that automorphism back. Okay, so this is not empty. I need to show that this is a group, right? Okay, what's the first thing that I need to show if I want to show that it's a group? Yes,
Closure?
absolutely. I think that's a day one thing we got to do is closure, right? We need to show that if I do these two, it's still equal. And by the way, I stuck those two together. What's the operation? It's function composition. That's why automorphism is important, because pitchfork goes from G to G, and then phi picks up where pitchfork left off. That needs to be in G. Otherwise, it doesn't make any sense to compose the functions. Everybody agree with that? So, okay, what does it mean to be still an odd? I need to show that this composition still not. So, what properties does phi and pitchfork have to have? First and foremost, it has to be a homomorphism, right? So you better check that. And let's check this first. If you look at phi pitchfork of xy, here xy are just two elements of G, right? This is phi of pitchfork xy. It's function composition. And what do I know? I know that this animal is a homomorphism. So okay, so far. I also know P is a homomorphism, so I'm going to do that again. P before X. P before Y. So in particular, this is so phi pitchfork XY is phi pitchfork X Y. So is a homomorphism. Okay with that? What else do we have to do? I mean, okay, we know that it goes from G to G, right? Because both pitchfork and phi do. What else do we need to show? I mean, it's not just any old homomorphism. We need to show it's bijective. And I'm okay with you appealing to 3190 or wherever you've been before, right? Because did you all learn, like in the proofs course or some earlier course, that if you have the composition of two bijective functions, it's a bijective function, right? In fact, you may have learned this. If you compose two functions that are one-to-one, it's still one-to-one. And if you compose two functions that are onto, it's still onto. So if you compose two things that are both of those, it'll still be both of those. Also, is bijective as both the well. So we've got the closure. Everybody okay with it? Okay, what else do we need? Got closure? Associativity. Need associativity. Somebody help me be lazy on this one.
Is function composition always associated?
Please don't make me grade your papers on this. Yes, function composition is always associative. This is another kind of background thing. You probably learned this or saw this when you did, you remember when you did like, relations in 3190, you did sets, you did relations on sets. That's where you see this. That's associativity. There we go. But, oh, I got associative. Anyway, if you didn't learn that, believe me now and believe me later, a function composition is associative. If you don't know how to prove it and you don't believe it, then come to my office and I'll be happy to prove it for you. But this is, you can take this as rule of law, that function composition is associative. Okay. Closure, associativity, what else? Let me do the easy one first. Identity, right? Notice that the IG is identity. Because if you do pitchfork IG or you do the composition the other way, that's not pitchfork. This is almost. Because when you plug anything to it, this leaves it alone and then you plug it into that. And if you do it and you plug it in here first, then this leaves that alone. So, yes,
Can you remind us what we're trying to, like, what is the problem we're solving again?
we're showing that the OG is in fact a group.
Okay.
Okay, so if we've got 3 out of 4 down. We've got closure, associativity, identity, right? Yes.
In the definition of OG, there's just the phi function. So can you explain where you got the pitchfork function from also?
Well, I needed to show that any 2 elements, when you combine them, are still in there. I didn't say that pitchfork was different than phi. It's just another possible element, right? In fact, at the outset, in odd G, I don't know, there may be only the identity in there. I'll give you an example. Take the group that's the identity. The only homomorphism in there is the identity function, right? And in fact, if you look at Z2, there are more than one homomorphism from Z2 to itself, but there's only one automorphism. And the only automorphism of Z2 takes 0 bar to 0 bar, 1 bar to 1 bar. That's the only way that you can do it. Because in any homomorphism, you have to take 0 bar to 0 bar. You have to take the identity to the identity. And so in that particular example, the automorphism group only has one element. But here abstractly, my pitchfork and my phi would have been the same element, but it doesn't matter because I'm doing it in a more general sense that works for the more specific one as well.
So are you saying that you're letting the pitchfork represent some automorphism on G, and then the same thing for phi, and then you're doing the function composition?
That's exactly right.
Okay.
That's exactly. Yes.
Can we just do function composition when present automorphism?
Yeah, that's right. That's right. And that's the function composition. You need it to be an automorphism. You need to be 1-to-1 and onto, and you also need to go from G to itself. Because if it went from G to H, so if you've got phi that goes from G to H and pitchfork that goes to G to H, you can't necessarily compose those because your phi will go into H, and then that's not even defined for pitchfork, right? Pitchfork needs an input of a G. Yes.
So if we're just showing that this is a group, then why did we have to show that it's a homomorphism?
Because if you have pitchfork and you have pitchfork and phi and odd G, what you have to do is show that when you combine them, it's still an element of odd G. That's the closure bit. So when you compose these 2 functions, how do you know this is still an automorphism? Right? And that's what we did here. First thing we did is we showed first, to be an automorphism, it's got to be a homomorphism. So we showed the compositions of homomorphism. And then go further, we need it to be bijective, right? And that's when we use that, the composition of 2 bijective functions for bijective, right? So I gave you 2 automorphisms, 2 potentially different automorphisms. You need to show that when you combine, it's still an automorphism.
I thought we were showing this group. Are we showing that their
That's right. And
composition is a group or?
no, you're showing when you, so you've got, so I think you're confusing the domain and the automorphism. So you've got a group G. Now you've got aught G, which are functions that take G as an input. These functions themselves form a group under composition, right? That's what we're trying to show. So I gave you, these are two functions that are bijective from G to G and are also homomorphism. And I want to combine them by function composition, right? So when I claim that this new composition is an element of aught G, that gives me the burden of proving several things. I need to show that composition is still a homomorphism. Because to be in club aught G, you have to be a homomorphism first and foremost. And that's what we did here. We looked at this XY, we broke it up, played it out. We said, oh, look, it's still a homomorphism, right? Okay, so far? To be in club aught G, you also have to be an automorphism. Now, we already know that the composition goes from G to G, so that part's covered. We also need to know it's bijective. But this is where I quote 3190 because both pitchfork and phi are bijective, their composition is bijective. Now what you have in our quest to show that aught G is a group is this. It's closed. If I give you two automorphisms and combine them, it's a new automorphism. We got to show some other things. We got to show that this operation of function composition is associative. Well, I cheated on this and said, oh, remember 31. We've got to show that this group of automorphisms has an identity. My identity here is this function IG that takes everything in G to itself, right? Remember that. Right? This magic function composed with phi in either direction gives you feedback. So now I've got the identity. So I've got 3 out of 4 of my blocks knocked down. It's closed, associative composition, and it's got an identity. Right? What's the last thing I have to do? Yes. I need to show that the inverse of any automorphism is still an automorphism. Right? So the last burden I have is showing inverses. That is, I will resist calling it phi inverse. This form, I'm going to call it that later. This is the last mountain we must climb. So, you have this on how we're going to do this. Absolutely. You all remember back from the 3190 days that whenever you have a bijective function, it has an inverse, right? Y'all remember that? That's what they care about. And I bet you also probably learned that if you have a bijective function that has an inverse, the inverse is also a bijective function, right? So, in fact, I'll tell you how it was defined. In 23190, we define, so I'm going to define the inverse function. Also from G to G. And I'm going to define, you see this defined in 3190. You'll actually see it like in the appendices, even in the calculus book. They'll say phi inverse of A is equal to B if and only if A is phi. This is the way the inverse function is defined. It undoes phi. So if phi takes B to A, the inverse function takes A back to B, right? That's exactly, it's basically the reverse gear of phi. That's what this is designed to do, right? Here's what I know about phi inverse. This is, you can quote that also at will. This is old knowledge in the sense that if you have the inverse, a bijective function has an inverse, and of course, so actually what happens is phi inverse is the identity, and this is phi inverse phi. And of course, from what I've said so far, this actually implies the phi inverse is also bijective, right? But there's one thing that I need to convince myself of. And what's that? That's right. What's not clear is this inverse function that we created in 3190, is it actually an honest to goodness homomorphism? That's what we have to do. We need to check. Right. So, any ideas on how to do that? Goodness gracious. Well, let's look at X, Y. Here, all my little letters, all my English language letters will be elements of the group T. I need to show, if this is a homomorphism, I need to show that that animal is phi inverse X times phi inverse Y. But how am I going to do that? Oh, dearie me. There's a number of ways to skin this cat, but any ideas on how I might press forward?
Do X prime of X, find that as X prime Y prime? Or do you have to start with define the of X prime as this?
Right. So here's what we know. We know that the phi, the original phi is an automorphism, right? So in the previous project. So here in the bijective part, I'm going to use the onto part. There exists A and B in G such that the phi of A equals X and phi of B equals Y, right? So X is actually phi of something and Y is phi of something. Everybody okay with that? So let's see what we can get away with here. All I did is I replaced X by what it is, it's phi of A. Replace Y by what it is, it's phi of B. Any ideas on how I might be able to move forward? You guys see anything I can do to manipulate? Maybe what's inside the parentheses now? There you go. I don't know phi inverse is a homomorphism, but I do know phi is, right? And that's the ticket right there. This is actually phi inverse phi of AB. Because that's a homomorphism. Oh, and now I totally got this one. right? Because what happens when I do phi and phi inverse? It should just give me AB back. Now, before polyps to solve, let me also remind you that this means A is phi inverse X and B equals phi inverse Y. That's what it means to be inverse functions, right? So now replace A and B what they are. Of that. And it's all the inverse of X, Y, it's the inverse X, the inverse. So, all right, G. Yes. Which is kind of cool. You've got now a group of functions. Everybody okay with them? Let's use that. Okay, I think there are other parts. You wanted me to dig in the other parts, didn't you?
Probably.
Okay. Define the piece of G by conjugation. Okay. Actually, the next one is a little bit easier, I think, than this one, maybe. Here is a particular automorphism that both fall for non-appealing rings. Let me say this. Take some G and G. So G will always be the same thing as I progress through this exercise. Define piece of G, G to G, D G of X is G X G inverse. And I believe the problem says prove that this animal is an automorphism. Okay. Okay, what do we have to do? Homomorphism, one-to-one onto, right? Do I agree with that? So let's just see where the good Lord takes us. P of G, X, Y is G, X, Y, G inverse. Right? That's just the rule. How might I move forward from here? Did you all get your questions answered before you got to go? Any ideas on how to move forward? Here, let me write this dramatically. Pretty dramatic, right? Groups here is elements of that. See what I did? Nothing up my sleeve. Because that orange thing in there is the identity, right? Everybody agree with that? But now I can sagaciously group this like this. And what is this? Well, this is just B G X B G Y. It is a homomorphism. This kind of little trick where you insert inverse pairs is really useful. Group theory is used for this trick a lot. Right? Okay, so far? Okay, homomorphism, got that. Leave one-to-one and onto it. For one-to-one, I'm going to do my favorite trick where we show, how can we show something's one-to-one? Show that the kernel consists only of the identity, right? So let's let X be in the kernel of BG. What does this mean? This means that phi g of x is the identity. And of course, the rule here is gx, g inverse. Now just massage this equation a bit. The first thing I'm going to do is I'm going to multiply on the right by g. This means that g is equal to gx, because on the right, the g will cancel this. Now multiply on the left by g inverse, and I get e equals x. So anything in the kernel is the identity. So kernel of phi g is the identity. So phi g is number one. That's the easier one, I think. The onto one might require you to think a little bit more. Any questions on that? Yes.
You could also just say that if you have some dx and py, they must be equal to a similar trick, so.
Absolutely, you can. In a lot of situations, it won't make much difference whether you use this technique or not. But there are some situations where the kernel trick shortcuts it a little bit. If you're talking about functions, if you want to show some function as one-to-one, you have to do the f of x equals f of y plus x equals y. But if it's a homomorphism, this allows you to do the kernel trick, which sometimes gets worse. It's never worse. Okay, how about on? Well, let's let careful choice. Let's let y equal g. B to find solve this times z g such that p g of t is equal to y. Any ideas what you might do?
C B G versus Y G.
Fantastic. I mean, all you got to do is find the appropriate things. And you'll see this is set up to behave like an accordion. This is G inverse, Y, G inverse. And at both ends, I have a G inverse, a GG inverse, GG inverse, canceling, this is Y. So B is bijective. And so therefore, so this is an automorphism. By the way, this automorphism is totally boring unless the group is not abelian. If the group is abelian, this automorphism is always the identity, right? Because if you conjugate something and everything commutes, then it doesn't do anything to it. Any questions? Final question is on this part is show that the correspondence G goes to phi G is a homomorphism from G into aught G, and what is this? So the correspondence G goes to phi G. Remember, with this I said I had a fixed element. So if I take a fixed element and correspond it to the automorphism that it creates by conjugating, show this is a homomorphism from G into aught G. What is its kernel? Okay. So I'm going to define, instead of just saying a correspondence array again, little silly arrow down. I'm gonna call this. And here's the way it's gonna work. Your input to capital pitchfork here is gonna be an element group. And it's got to barf out an automorphism. And the automorphism that barfs out is this. We've shown this is a group, we've shown this is a group, show that this function actually gives you a homomorphism. Everybody cool with where we're at on that? Now, before I formally show that this is a homomorphism, I can kind of see what's coming. So I'm gonna make an observation here, prove it. So I claim if G and H are in G, then phi of GH is phi of G E of H. Okay, so what am I saying? I'm saying that if I take the composition of the automorphism determined by little h and then compose it with the automorphism determined composed by G, I could have just in one step done the automorphism of GH, right? Doing the automorphism conjugation by H, then conjugating by G. It's the same thing as just conjugating as GH in the first place, right? Let's verify that this is true. If you look at phi of pH, what does my rule say? That this is GH, X, GH, and but I'm go over that. So I'm going to do my usual thing. I'm gonna break out that -1 power. I agree with it. Now notice that this thing in the middle is this thing right here is phi H X. Right. But this is just phi G doing its business to this. So this is actually phi G doing its conjugation for it. G, that thing G inverse, pH notes. Right there. So I proved what I needed to do because notice that PGH acts on X the same way as this composition is. So what PGH does is the same thing that you would get by decomposing them one by one. Right? Okay with that? Really, you may not notice it yet, but what I've done is I've really sort of done the heavy lifting already on this. I want to prove the capital pitchfork is a homomorphism. So if I look at capital pitchfork of GH, by my rule, this is a function phi GH. And what did I just prove? That that's the same thing as phi G phi H, which is pitchfork P, pitchfork H. That's all we need. Well, that's all we need. So capital pitchfork from G and dot G is a homomorphism. Everybody okay with that? Okay. What is its kernel? I think was the next thing. Well, I guess it's a set of G and G such that so it's everything, let's see, that ends up with the identity automorphism, right? Do I agree with that? Let me see if I can think of this better way. So kernel capital 4 is a set of G and G such that E is that G. Think of another way to kind of characterize this. Such that right. So pitchfork G is actually this thing, which is actually conjugated to G. So it's the set of every G and G such that this is Pg. This has to be the identity function, so this has to always be X. Does anybody see what this is?
We're all normalized.
Oh, you're close.
The center.
And G is such that, let me massage this a little bit. Such that GX was actually wrong.
Yeah, the center.
But it's the center, that's right.
There we go.
This is the center. Thank you. Okay. Yes.
Can you explain what's the difference between saying something is a correspondence and then saying something is like a projection or like mapping to something?
Okay, so you hear these things like a one-to-one correspondence, that might be what you're asking about. When you hear a one-to-one correspondence, that means there's a bijection. So like, for example, today in class, we had a theorem that said there's a one-to-one correspondence between the subgroups of G that contain N and the subgroups of G mod N. That means there's a bijection between those sets. Right. So in other words, it's sort of like the 31-9 thing where you use functions to count sets, right? Whether they're countable or uncountable, or anyway, a one-to-one correspondence. When you hear that word one-to-one correspondence, what that means is it's bijection of sets. A correspondence is just like a function. So if you're asking about what happened in this previous problem, the problem's worded show this correspondence. A correspondence in that sense was used as a function. Your input was G. Your output was phi of G, which is just some element of aught G. And so show that correspondence, show that function is a homomorphism. Okay. Other questions? Yes. You can tell me what it is because I can look at it. That's easier for me.
25.
Let me see here. So, where are you? Which year is it?
20.
25? Exam?
Yeah.
Okay, what question is it?
Number 3.
Oh, right. So consider the symmetric group on the set of 3 elements. Does there exist a surjective homomorphism from S3 to Z? Okay. So here we have S3. We may not need this, but I'll write down the elements. Is there a surjective? That's important. homomorphism. B from S3 to I might as well not ask the question without any modifiers, because there's certainly a homomorphism from S3 to Z3. In fact, there's a homomorphism from any group to another group just by taking everything in the domain to the identity, right? But it's super boring. The question is can we cover Z3? What do you think? Suppose yes. Suppose we can. So you have B, S3, C3, and it's on. What does the first isomorphism theorem say? Well, it should say that S3 mod the curve phi is isomorphic to the image. But if it's on, what's the image of phi? Should be all of Z3. Agree? Somebody explain to me why this is possible. By the way, I think he talked about this earlier. Can anybody tell me what are the normal subgroups of S3? Okay. So you let me get the easy ones. Always the whole group and the identity, they're always doing this. There's actually one more. And only anybody know what it is?
E and vector chambers.
Everything with it. Maybe. Oh, Ian. Ian, what else?
Something about it. Right.
Actually. That's the only. Look at. What's the index of that group? How many elements are in this group? This little subgroup? There's 3, right? How many elements are in S3? There's 6, right? What's the index of this in S3? It is 2, so it has to be normal, right? Remember that old chestnut? This is the only normal subgroup. In fact, there's 3 other subgroups: EN1,2, EN2,3, EN1,3. None of those are normal. In fact, we proved that one of them wasn't normal and the other 2 aren't normal either. Now, if there's a subjective homomorphism here, there has to be an isomorphism from S3 mod kernel phi to Z3. This has order 6, this has order 3. So what would the kernel of phi have to have order? What would the order of the kernel of phi have to take? That would be 2. Agreed? And the kernel of phi is always normal subgroup, right? S3 has no normal subgroups, so it can't have. Uh, but S3 has no normal sum. In fact, the only normal subgroups are of order 1, 6, and 3. So that means, if you use this idea again, that if you have a surjective homomorphism from S3 onto another group, that group, if it's surjective, that group has to have order 6, 1. Well, that's of course, or 2. I agree. Because the kernel can only be one of those normal subgroups. If the kernel is the identity, then this thing would have to have 6 elements, right? So it's surjective onto a group of order 6. That's a possibility. If the kernel has all 6 elements, that means this is the trivial group, and this has order 1. So it's surjective onto a group of order 1, which is more. Or the kernel could be this exotic subgroup of order 3, in which case the image could have 2 elements. And I think that partially answers the next question. It's a matter of time. Any questions? I think that was actually kind of a tough one. That's the one on the test that I think the students last year struggled the most. Yes.
So when we are writing this proof, do you want us to put more like clarity, I guess, into it, like more reasoning, like on the test, if this was like a question?
Oh, if you were actually writing this up yourself, what I would do as quickly as possible is I would say, suppose yes, so there's an onto homomorphism. Then I'd say, but the first isomorphism theorem means this. And then I would say something about no normal subgroups. I'll give you some advice on doing proofs on the, if you're writing this up for homework, yes, be detailed, et cetera, et cetera. On the exam, I want you to make sure that you give the old college try to everything, right? You don't need to write the great American novel on the exam. In fact, it's impossible to do it. Try the problem, and what I would do is I would get the bare bones explanation. I mean, I don't write it in Mandarin or something, right? I have to ask my wife to read it to me, but get it a little bit, just get the bare bones out there, get the ideas out there, and then move on. And then if you get to come back and polish, right? Also, for sure, folks, listen, I know it may sound childish, but make note cards, whatever it takes for you. Get those definitions down, because in fact, I think I've got it partitioned the same way I did last year as far as points. Pick the low hanging fruit. You do not have to write the definitions and stuff all right exactly the way I do in the book, but they've got to be right and they've got to be correct. Don't leave out the details, et cetera, et cetera. Another thing is, I get this kind of question all the time too. If I say, what's a group? One possible answer would be a group is a non-empty set that is closed, has an identity, has associative operation, and inverses, right? That's probably not enough information. If you're in a hurry to write that, you need to come back and polish it later, right? What is an inverse, right? When I first wrote up the definition in the notes, look at that, right? Because I do say this is what an inverse is, et cetera, right? Be complete as you can on the definitions, and just make sure that you pick that low hanging fruit. Yes.
What else would you want us to add to that definition to make it complete?
Oh, like so, if I was writing it, no. Well, right. A group is a non-empty set. G such that you can say something about a binary operation, but this will be more complete. For all X, Y, Z, and G, number one, I'll do 0. X, Y, is a dynamic set G equipped with operation. Such that for all x, y, z, and g, x circle y is in G, x circle y circle z equals x circle y circle z. 2, there exists E in G such that E circle x equals x circle E equals x. And 3, for all x in G, there exists Z in G such that x circle Z equals Z circle X Z. Now, I promise you that would be 4 points. All right. You have to do all that for 4 points. It depends on how well you write. All right. I am not looking for length. I'm looking for completeness, and those are sometimes two different things. Yes.
Is there like a rule of thumb for when we need to show well-definedness, like?
I can't do something that's, I will tell you this, if there's ambiguity about the input, right? Like when your input is a coset and you're defining it via a representative, then for sure you're going to need that, right? If there's any ambiguity about what this output, so what you're doing when you're trying to set up a function is you're making a rule, right? So that anybody that comes along and uses your rule will get the same answer, right? So here's what so for example, okay, this is actually an isomorphism. Okay, so here, this is the way that I used to write. This is the clock, right? 1 bar plus 2 bars, 0 bars. So you know how this one works, right? Okay. And what I want to do is this, of course, is the set. Those sets n plus 3 is n in the universe. Right? Now, my rule is going to be b n plus 3z is n bar reduced multiple. Pick a coset format. Just give me an n and the integers, doesn't matter.
2.
2. Okay. So right, that's what this rule says. It takes whatever it finds here and it says, okay, it's going to be 2 bar. So yours goes to 2 bar, right? Over here, see 3. Now, I'm going to pick a different coset representative than you did. I am going to pick -7. I can do that. Now, we were actually picking the same thing, right? Because notice that -7, what happens if I add 9 to -7? I get 2, right? So her 2 is in my coset, right? And if you subtract 9 from 2, you get -7. So her two is in my coset and my -7 is in hers. So these cosets overlap, so they have to be the same. But nonetheless, I'm going to pick a different representative. And we got to make sure, because on the surface of it, you and I got two things that look different, right? But they are in fact the same, because -7 is equivalent to 2 mod 3, because 2 minus -7 is 9 by 3. So mine also goes to 2. So that's what I mean. My function here, and this is a simple example, hinges on what representative. You pick 2, which is best representative, and I pick -7, right? Even though mine is kind of sloppy, it's still represented the same coset. We have to make sure that that comes out the same. Right? In fact, one of the big things that remember when we did quotient, right? And the first thing we did is we said, okay, x, the coset xn comes to coset yn, coset xy comes, right? The reason that works is the reason that always makes a group pretty plain and simple, as long as that multiplication rule I just gave you is well defined. And if n is not a normal subgroup, then you and I could pick different representatives of the same coset like we did here and get different answers if n is not a normal subgroup. And so that's why the well definedness is important. So if there's any ambiguity, right? If you look back at this pitchfork thing, you remember the correspondence we just did? There is no question this is a function. Input G, output this. There's no ambiguity there, right? Because I'm picking just a particular element. I'm telling every single distinct element in G where to go. You go to feed G. Your G and my G might go to the same thing. It doesn't matter. Where it goes, there's no ambiguity, right? This is why, you remember in calculus when you start doing stuff with square root functions and they said, oh, we make sure that we always take the positive square root, right? And you always take, that's because if I ask you, give me a number that squares to 25, that's not really a good question, right? If I said, give me a single number, because some of you in here may answer -5, which would be a correct answer to my question. That's why with the square root, you've got to pick one. Because if you just say, oh, my input is a number, a positive number, say, and my output is going to be something that squares to it, that's not well defined. Because if you give me 36, I'll say, hey, wait a minute, there's 2 things that square to that. Which one? Because the function has to have unique output. Does that make it worse?
Yes, no, that was great. I guess a follow-up question I have is like on the exam, like I understand that when we like write a function ourselves, like homework, it needs to be well defined. But like sometimes, like is it ever gonna be like the question gives a function and then I'm making a statement about that function, I need to show that it's well defined? Is that?
I mean, I would not completely discard that as a possibility, but that's more likely to show up on the homework. Because remember, I've got a grade, so maybe I don't want to read it. I'm not going to try to trick. And I think that most things I'm saying that they're probably not going to have to worry about that too much, but. We did encounter something today when we did third isomorphism that we actually did have to show well defined. So if there's ambiguity about the way the function works, you need to verify that it's a function, but not just correlation. Yes.
A specific question that probably doesn't matter, but on the exam for the definitions in problem 25, you ask what does the classification of cyclic groups say? And it says that is if G is cyclic, then what can you say about G?
Oh, yeah, that sounds a little open-ended. And actually, sometimes these questions will work. Somebody may have asked me to clarify. But here's what you can say. If I walk up to you on the street, right, so did the question say something like, if you have a group and it's cyclic, what can you say about that group? Okay, here's what you can say. If you walk up to me on the street and say, I've got a fifth group, I can say, if it's finite, it's isomorphic to Z mod n. Right, for some natural number n. And if it's infinite, it's isomorphic to Z. That's it. That's what the classification theorem says. If you have a cyclic group, if it's infinite, it's isomorphic to Z, and if it's finite, it's within elements, it's isomorphic to Z mod. Other questions? Yes.
For the example that you did on the board, can you explain why, like the C and the 3Z is equal to the set of n plus 2 for all n?
Oh, it's right here. Why that is, so, right, so suppose. So I'm gonna take you back to like more general notation. If n normal G, then is this familiar to you? When G mod n is a set of little g n, where G is G, with multiplication given by G1 n times G2 n equals G1 G2 times. That familiar to you? And that's what this is, G mod n is. Right? This is the same stuff here, right? The only difference is the groups abelian and I used additive notation. So here, the role of G is played by Z, and the role of N is played by 3Z. Right? And so this is just, instead of little g times N, I'm going to say little g plus N. Right? Because instead of multiplying the coset, I'm adding, because my operation here is additive, it's abelian. And so in this case, it would be where N X and Z. So if you look, that's the same translation here. Right? Instead of G times N, I have G plus N because the groups are abelian. That's the standard way that it's written when you're abelian. So it's the same thing, it's just translate to the plus operation instead of writing the addition operation.
Okay.
So it makes sense. Other questions?
For the question previously talked about, open 3, 4, the second part of that, we had that G, and you said that G in there is a fixed G.
I'm sorry, which one? Are we talking about 3B on exam from last year, or is it something else?
No, homework 3 this year.
Homework 3 this year.
Okay, question 4, that's the one.
Okay.
You said that G in there in the Fiji is fixed.
Mhm.
What about the notation tells you that it's fixed? Because often when we use little g, it can represent interchangeable G.
Right. I said it was fixed to emphasize that because what happens is I didn't want to use G goes from G to G. And see, it's confusing because this is also an element of G. Right. And so when I said it's fixed, I just mean that I mean, this is not where things are changing. Right, this is where things can change. This is the input to the function here. Right, this is where we're plugging the stuff G. And for every G, little g and G, there's one of these, right? There's phi sub G1, that's one function. Phi sub G2, that's another function. But for every one of those fixed GIs, it's not the G that's changing, it's the X, right? That's what you're plugging into the function.
So when we showed for the that PG is an odd G,
Mhm.
we showed that any G is an odd G.
That's exactly
By
right.
some single.
That's right. That's right. So we did that for a fixed G, but what we did shows for any G and G, that phi G is an odd G. That's right. Yes,
You have time to do number 3 from homework 3?
3 from our homework 3, right? Like this semester.
Yeah.
Oh, right. It says consider the subgroup of S9 generated by. One seven three trying to 6. With 6. Oh, 156. Yeah. And the question is, these are of course elements of S9. You can think of these as elements of S9, right? And so if you take these two letters, X and Y, that are written out this way, if you make any possible word out of X's and Y's, this form, and they're inverses, right? But by the way, I don't need inverses here because what's true about X and Y? It's the order of X. 2. And that's the order of Y as well. So both X and Y are their own inverses. Right? And so we can just make words out of X's and Y's and their inverses, which is just X and Y again. And this will form a little subgroup of S9. Right? Because everything you can do with this is already inside S9. What do you know? So in particular, the group generated by X and Y will be a finite group because it lives inside of S9. And although S9 is very, very large, it's still finite. All right. What do you know about a finite group generated by two elements of order 2? That's probably homework previous to this, I would say. You better remember?
Is that number 2?
What's it?
Does it also have to have orders, or it has to be a multiple of 2?
No, actually, in fact, unfortunately not, because again, you've got the problems with commuting. All the one said that the X and Y probably don't commute. Do y'all remember that homework problem? I think it was homework 2, maybe. Any group generated by two elements, any finite group generated by two elements of order 2 is dihedral. So this has to be dihedral.
I thought that just went over any group generated by one element of order 2. Is that?
Well, if it's generated by one element of order 2, it's just a group of order 2. And that's it.
Oh, okay.
And actually, you could reference the old homework in that proof. That the group generated by X and Y is the group generated by X or Y and XY. And this played the role of S and this played the role of R in the dihedral group. So again, this is a convenient time to practice this. 1, 7, 3, 5, 6, 2, 8, 1, 5, 3, 6, 4, 9, 1, 9. Let's see what this is. Where does 1 go? 3. And 3 goes to 2. 2 goes to 8. 8 goes to 6. 6 goes to 3, back to 5. 5 goes to 1, 7. And 7 goes to 1. So it closes off that cycle. 1, 2, 3, 4 is the first thing that we haven't seen. And 4 and 9 are disjoint from all these. So 4 goes to 9, 9 goes to 4, and that's all the numbers. I agree with that. What's the order of this element?
Element. Or equal.
So I can answer all those questions now. The rotation is of order 14. So it's the dihedral group on the 14 guy. So the group that generates is D14, and it's got 28 elements. And I think those are all the questions that were asked. Does that make sense? It's kind of interesting because in S9, even though it's a big group, the biggest single cycle you have is only 9 elements, right? Because there's only 1 through 9 in there. So the biggest single cycle is 9 elements. But so you would think that maybe that means that, oh, maybe the largest order element is 9, but that's certainly not true because this thing lives inside of there and it's got order 14. So you can actually fit a dihedral on 14 on it.
You would say that the subgroup generated by XY is isomorphic to 14.
Yeah, so generated by X and Y is isomorphic.
Can you explain why?
I'm sorry.
Can you explain why? It's
Well,
isomorphic?
because of that homework, because of the previous thing. So what we know is this. We know that this is a finite group. It's finite because it lives inside this finite group. So that's what finite. It's generated by 2 elements of order 2. So in our earlier homework, we know it has to be dihedral. So I already know it's dihedral. Okay, so in that homework, it was also shown that the group generated by X and Y is the same thing as the group generated by Y and XY. And this XY played the role of R. To know what the dihedral group is. So now that you know that it's dihedral, all you need to know is the size of the GOM that it's on, right? And XY is the rotation. That XY we got there is of order 14, so it has to be a 14 GOM, right? So that means it's dihedral on that. Does that make sense?
I just don't understand how like it being isomorphic comes into play. Because when I think of isomorphic, I think of it's a homomorphism. So there's like that definition where it's
Well,
like,
there is, right? And I'll show you how you do it. Uh, here's the way it works. And now, all you have to do is expand this out using factors. Right. And so any element of D14 is of the form P of R S to the A. It's a word that you put in that form, which is P, the R to the M, P of S to the A, and just replace P of R with this cycle and take that to the M power, and this product cycles here, and take that to the A and take the power. I mean, there is an isomorphism. What we proved in that homomorphism is, or what we proved in that earlier homework is, and another way to see this, that it's isomorphic, is if you take that strange 7 cycle times 2 cycle here, and well, we'll just do it. We'll use the thread here. X, Y, Z. So let me show you that this actually works. This is more complicated. But this is the same principle as what we were doing before. Is that me freaking out or what's going on? Okay. Is it neat? It must be. Yes. You want to think about the quit or something. Well. Let's explicitly do this. So S is 2, 8, 1, 5, 3, 6, 3, 6, 4, 9. And then the R is 1, 3, 3, 6, 5, 7, 4, 9. And then I've got to do that again. I've got room 2, 8, 1, 5, 3, 6, 4, 9. Let's go through it. 1 goes to 5 to 7. It's done. Five, 7. That's right. 7 goes to 1, 5. 5 goes to 1, 3 to 6. 6 goes to 3, 2 to 8. 8 goes to 2 to 8, 2. 2 goes to 8, 6 to 3. 7, so 2 better start 1. 3 goes to 6 to 5 to 1. Good. And what about 4, 9? Well, yes, so 4 goes to 9, 4 to 9, and 9 goes to 4 to 9, 4. Bang. Notice this is R inverse. So it's dihedral. Right. So I think the wording I use in that homework will show that any group generated by 2 elements, finite group generated by 2 elements or 2 is dihedral. So it satisfies those relations. But that means that there is an isomorphism. Please don't do a small example. Don't sit here and figure out where all 28 elements go. But if you do, you'll see it works. It's actually a homomorphism, and it's one we want to know. Does that kind of clear it up a little bit for you? Okay. Others? Y'all maxed out tonight?
Yeah, I just thought that actually.
Not really, might be up all night doing it, but.
Oh, yes, I will.
If you're gonna be up all night doing it, be up all night tonight, but don't do it the night before the exam.
Well, I'll be up all night doing like definitions.
Yeah, me too.
So that's
what-
probably my
Always on it.
Yeah, exam, actually.
This girl took calculus with me, this is many summers ago. And she was like, she was about to graduate, she was real smart, she was a biology major. She was very confident, there were like younger kids in class, they kind of fluttered around her a little bit. Because, I mean, she was good to work with. And, they would come to me at these strange hours. And, you know, they work with her while they came to me, like on the night before exams, they come to these strange hours. And I was like, well, why aren't you working with her, right? Because they always work with her. She goes, we can't work on it the night before the exam. And I said, well, why is that? She goes, because apparently she goes home and she goes to bed at like 6 o'clock. And I asked her about that. She goes at 6 p.m. She goes, well, I go to bed at 6. I get up at 2 in the morning. She goes, because I can't really properly prepare for the exam without the pressure of being that day. It's like 2 in the morning. So, you know, whatever works for you, right?
Hi. Maybe that's the trend, right?
Well, not, it's the same.
I actually felt more confident.
No, it's-
Really?